Morning, everyone. Let's continue the topic that we started yesterday. As you remember, we started with linear models, and we look how those linear models can be trained to solve regression problems, and afterwards adding on top of linear model a small piece of nonlinearity, which was a sigmoid function. We managed to approach classification problem. So it was kind of illustration how one model can be converted to algorithm query. And currently we're going to see maybe the opposite direction. So we start with classification problem that is naturally can be solved by decision trees, and we'll see how decision trees can also be applied to solving regression problems. And we'll look into different ensembling algorithms. How can you combine two different pieces of algorithms and plug it together to solve a single problem? It will be theoretical part, and practical part will be focused on applying those, practicing building those trees, and we'll focus a little bit on applying those techniques to particle identification problem in particle physics. Being more specific, we're going to start from decision trees, and then we'll go through some of the families of decision trees. So there are many different kinds of those, but we select probably the most interesting, the most popular ones that you can find in many applications, and it is very helpful to know how those trees are organized. And as I said, we will follow to generalization of those models to a stacked version. So how you can build an ensemble of those trees. Okay. So speaking of decision trees, it's quite intuitive structure for making a decision. That's where the name comes from. So imagine you want to get a loan from a bank, and bank has to somehow encode the rules for giving you this loan. So it is a very simplistic one, but you see there are several features that are analyzed through the questions. So features are, as you see, is age, it is a salary, it is experience, and it is a binary feature if the person has other loans. And there are, you see, red nodes in the decision-making process that check those features against some properties, against some thresholds. So, and depending if the value of the specific feature is above or below this threshold, you go on left or right. So that's why those trees are called binary trees. So they replicate a binary logic that is quite natural for making decisions by humans. Well, it is not the most natural, but it is quite easy to grasp. Okay, and besides red nodes, there are blue nodes, or as they called leaves. They correspond to the final decision that the tree does. In this simple example, decision is also binary, either reject or grant. But in reality, those decisions can be an arbitrary value. So imagine an analogy with a probability. So it could be some kind of weight that replicates the confidence of the algorithm in specific decision. So if you encode those decisions into the range from 0 to 1, So a real number between 0 and 1 would correspond to the weight of the final outcome. So if it is close to 0, close to 1, the tree will be more or less confident in what it does. Otherwise, you should do something else. Maybe call a human assistant or bioworker that would help to resolve the case. Okay, so let's have a look at the formalism that is introduced by those trees, or that is needed to understand those trees from algorithmic perspective. So we say we have a decision tree V. If we have a structure that contains internal nodes U that belongs to V, and with every node there is a predicate that evaluates all the features of our objects and computes the number either 0 or 1. And also there are leaf nodes in this tree, and output or value that sits in those leaves is the prediction. So, and if we want to evaluate some object through the tree, so we compute, we start with the root of the tree, which is called U0, and we compute the predicate output B that is either going to be 0, and if in that case we go to the left, otherwise we go to the right. So either we go here, or either we go and then we can go here. And if we end up with a leaf, then we return the value that is stored inside this leaf. So in practice, we usually choose the predicate of this form. So we compare the object and feature of number j in our feature set with a threshold t. So essentially we evaluate the following thing. So if we see if the value of this feature is less or greater than a given threshold. Okay. So how can you build such a tree? So we start as yesterday with a training set. So it is purely data-driven algorithm, and we greatly split this training set into two different subsets. So you see that the decision for splitting this whole set into subsets is performed over specific feature number j and specific threshold value t small. And by greatly split, we try to minimize or optimize a given loss function. So we demand that the loss computed over the whole tree should be minimum. So we create an internal node at the second step. We created an internal node corresponding to the predicate that matches the condition of the previous split. And if a stopping criterion is satisfied for U, but stopping criterion it means that we do not want to split this node anymore. This stopping criterion may depend on the depth of the tree, may depend on the value of the threshold or some other condition. So it is up to the algorithm definition how to define this stopping condition. Usually, it is corresponding to the depth of the corresponding node. And so if it is a leaf, so we find some specific output that belongs to the space of the predictions and assign it to this leaf. So it is here denoted by CU. For example, it could be a ratio of positive and negative examples that we end up in the corresponding subset. So we just compute this ratio and store in the leaf. So, and if the stopping criterion is not met, we repeat the steps 1 and 2 iteratively for those subsets in R1 and R2, and and we get the decision tree that has all the data classified into those leaf nodes. So here is the illustration. Here is the illustration how we start with a data set that contains red dots and blue triangles, and we want to find an initial split. So we have two features, the horizontal line and vertical line. And we can do split either horizontally, so it can go like this, or it can go like this. So you see it is a line that goes along the whole dimension, or it could be a vertical line, so you can split it like this. We see that degree of separation red from blue is much better if we do split horizontally. Well, if we do split horizontally within the range. So if we split it vertically, it doesn't make much sense because the fraction of blue and red on the left and the right would be the same, no matter what split we choose. But if we choose a horizontal split like this, it would be almost ideal. So the quality metric of the tree built along this line would be ideal. And that's what we see on the picture on the right. So we make a split and separate the whole data set into subsets, R1 and R2. And this is mostly it. So we can then refine our splitting criteria, splitting scheme, and try to cut pieces from here like this. If you remember about the fact that the data is prone to error, so there might be some noise in the data. So you might do not want to go for those red ones because most likely they are below the split line because of the noise effect. Okay. So in this more complicated scenario, it is not that obvious how to make a split initially. I would instead, looking at this, make a split maybe like this. But okay, so you see the algorithm. The algorithm made initial split here, so it was initial split. Then probably decided to make a split here. Then maybe decided to make a split here, and then here, then it goes here and here. So it is set of splits that separate red from blue into different nodes. So every square at this picture corresponds to a node of the tree. And as you remember, we record in the leaf node the ratio of blue and red items. So that's how it usually works. As I said, it is also looking at the previous example, it is also quite easy to try to catch the items that may be coming from the noise from our data, right? But if you run decision tree algorithm long enough, so you make many splits, you could create such a split scheme that would cut small patches of the surface that would contain only colors of items of a certain color. And on the training sample, the accuracy of such splitting scheme will be ideal. So it will be it will be just 100%. But you remember, if you add more data and data comes from the distribution, that usually is not that peculiar. So there are no such small patches coming from those those distributions. So unlikely that there are some such strange effect. Most likely, your quality, algorithm quality, will be less, smaller. And this is called overfitting, and with decision tree there is it is very easy to build such a tree that would result in overfit pattern. So let's take a look at kind of decisions that we have to make to build those trees and run those effectively. So we have to understand what kind of predicates do we want to for internal nodes. Then we have to understand that what should be the loss function for the whole tree, and what should be the stopping criterion for turning a node into a leaf. And there are various hacks that deal with missing values that allow to remove unnecessary complications inside the trees. That is called pruning, like removing parts of the tree. So generalization error will be higher and performance would be faster. And the examples of the algorithm that rely on different kinds of the decisions are mentioned here. So it could be CART, C45, ID3, whatever. So let's take a look at the loss function example. So imagine we have a subset at the M step, the subset Rm. So remember, we split into our initial data set with every split into two subsets. And with the current split, we have our RL that correspond to the left. It is just a space subset, and this should be R, of course. RR. That is also a subset of Rm, and it's correspond to the right direction, to the going to the right. And then we choose a predicate to optimize. So it could be the following predicate. So it corresponds to impurity. Roughly, impurity is number of fraction of different nodes in the same fraction of different instances of classes of instances in the same node. Or R here is a loss function that we compute for our classification algorithm. So it's kind of a measure of the bad separation. So and the predicate that we may want to optimize is the following. So we compute impurity from the initial split and subtract impurity normalized to the number of nodes that we get if we split at the specific feature J and specific threshold T, right? So and we want to maximize this thing. So we want to make it as pure as possible. So if we from initial impurity subtract impurity of the resulting scheme, so it should be, the bigger it is, the better. It means that our splitting has given us much better purity. So, and this is the illustration I was talking about. So before we had something like this. So in that case, we have 3 instances, but 3 classes, but it doesn't really matter. So we select a splitting condition that maximizes gain of purity, and we go into something like this, and we have purity after split. And so we want to go into as pure separation as possible. Speaking of information criteria, so it is a purity condition, purity mathematical expression. So for regression case, so this, as I mentioned, decision trees can work for both regression and classification. And for regression, it could be something similar to the minimum squared error. So you see, it is a value stored in the leaf. It is some kind of output that we get from our algorithm, and y subscript I is a ground truth label. So so we compute sum of squared residuals minimized by C, and in that case, impurity would be the variance of the target that we get inside the node. And for classification, it is similar to accuracy. So it is a share of predictions of equal number, of equal class. Sorry, so we choose this number pk. So it is something that corresponds to the accuracy, and miss rate then can be expressed in the following way. And so we have to minimize a missing rate somehow, 1 minus p pk. And there are like popular examples of minimization minimization criteria. One is called Gini index. So it is computed in the following way, or it could be a cross entropy. It is similar to classification learning target. It is minus and this sum of pk multiplied by log pk. And final building piece of decision tree is a stopping rule. So it usually quite significantly impacts the learning performance, and there are many choices you can make. So as I mentioned, the most popular is about maximum tree depth. Also, it could be about minimum number of objects in the leaf or maximum number of leaves in the tree, or we can stop if all objects fall into the same leaf, or so we don't have any alternative. Or if we see that the quality improvement is going below some threshold. So usually with the training of our model, the quality, well, maybe in terms of accuracy, it grows gradually. Sorry, it's a dashed line because I'm using such an instrument, but you probably get the idea. So you start splitting, and quality start to increase, but at some point you saturate your quality, and maybe it is a good signal to stop adding more leaves if the increase of the quality at every split falls below a certain threshold. And typically, particular values for such decisions. So for every choice you see here, there are some parameters that you have to specify for algorithm before it starts. It is called hyperparameter. So like maximum tree depth, you can choose it to be either equal to 5 or equal to be 10. And depending on this, you get different quality. And a priori, it's very difficult to specify what should be this hyperparameter value. And one of the workable approach for those hyperparameter choice is selection by grid search or random search and cross validation. So we have to try and see. So it is trial and error approach. Or another thing that can be helpful here is called black box optimization. Maybe we'll have time to cover those algorithms as well, but it will be later. So another important thing that can be operation can be performed of the trees is called tree pruning. It is about removing unnecessary nodes, unnecessary splits in our tree, and then by this we can refrain from overfitting our tree. So it is kind of structure optimization of removing least important nodes. Okay, so that's basically the main building blocks of a decision tree algorithm. It is quite intuitive because it replicates how people think or how people argue with each other. So it is very long tradition, probably rooted in ancient Greek times, or maybe before. It's a suitable algorithm both for classification and regression, and one of the very strong feature of this algorithm that you can interpret the result. So if you know exactly at what node your algorithm is stopped, you can backtrace all the decisions that it made. And nowadays, as you imagine, it is becoming a very, very hot topic because everybody is obsessed by a black box making false decisions in the field of artificial intelligence. And with neural network, you do not have such a luxury usually of tracking back the properties of particular decisions to the features. So of course you have a lot of computational nodes that are interlinked with each other, and so you see that the data mostly all features are contributed to the particular decision. But in decision trees, it is not the case. From the training sample, see clearly what features has contributed, and moreover, you can also assess the importance of individual features by number of splits that you make along this feature during the building of the tree. So if let me scroll back to the example. Yeah, so maybe it's not the best example, but just to illustrate. So you see that along a horizontal axis you have 1, 2, 3, 4 splits, and along vertical axis you have 4 splits, and along horizontal axis you have just 2. Well, it means that the structure of this tree has something interesting to note about this horizontal feature. So it means that this feature may be of more importance than this one, than vertical one. So and you can compute this importance for every feature by looking at the decision tree structure. Also, it is quite non-demanding in terms of pre-processing. So you can build data without introduction of some normalization, because it doesn't matter if you transform your feature from linear to logarithmic, or you do some transform it to something similar to Gaussian or whatever. But the main drawback of the decision tree is it is prone to overfitting. So depending on the training sample, it can become not it can introduce unnecessary complications and noise that is not relevant to the distribution our data coming from. And all the examples of decision tree extensions that we're going to look at now will be designed to deal with this instability, this overfitting. Okay, so let's look at the embedding and random forest example. Maybe if you have any questions, since we're now in interactive event, not streaming, maybe you want to ask something that would add some interactivity to our class.
I have a question.
Yeah, sure.
The decision in a leaf is based on a single feature of an instance. I mean, you cannot combine it like a multidimensional function or something like that, for example?
In the basic implementations and the implementation that I'm going to talk about now, it is true. So I believe that there might be some complicated versions of decision trees that take into account many features, or maybe doing more complicated non-linear, using nonlinear function transformation for every tree, but those are not very popular. So I'm not I'm not aware of any good examples that would be robust and performant, as robust and performant as ensembles like bagging and random forest, for example. And you can judge how popular machine learning algorithm is by looking for maybe at Kaggle competitions, and you can see how many times it is used by different competitors at different challenges.
And I have a second question. Maybe this is...
Yeah, sure.
So the cost function, well, I'm maybe super biased because I always think of problems in terms of signal and background. So two different nature of the instances. But when you define the cost function, it was a little complicated because you want to maximize something, but if you have, for example, three different types of instances, essentially the decision tree, the goal is to separate each of them individually, or just to maximize one of them that you choose as your signal, and then all the others go in whatever.
Yeah, so it is it doesn't very well suited for multi-classification problem. So if you have two kinds of background and one kind of signal, for example, it is not naturally suited for those kind of problems. So I need to check if there are specific version of decision trees algorithm in scikit-learn. So as you remember, scikit-learn is a reference implementation of most popular algorithms. So if it contains good examples of multi-classification decision trees, but usually what people do when you have several classes, you train an algorithm. So you train binary one versus the rest, or one versus each other. So if you have two backgrounds, so you train a tree that separates those two backgrounds, and a tree that separates signal from background one, and a tree that separates signal from background two. But I guess that it is not difficult to extend the formalism I mentioned to the case when you want to deal with three classes, and just you want to make a purity of the separation as high as possible. So variance of the class instances inside every leaf node as low as possible. Right. So it seems to me quite natural extension.
Okay, thank you.
Okay, so let's go further. So we introduce some ideas first, some algorithms that not specifically designed for trees, but used in the context of trees quite extensively. So the first procedure is called bootstrapping. So imagine we have a sample of items with labels, and we want to generate a new samples or subsample from our initial one, drawn uniformly at random with a replacement. So it means that the same instance can go into our subsample, into this guy. Right. So here is the illustration. We have initial data set, and we subsample it into x1, x2, etc. And then we train. We can use those subsamples to train different learning algorithms. It could be whatever. In current case, since we're talking about decision trees, we will train decision trees. So with initial, it could be whatever. So we learn our n decision trees from those subsamples, and then we average predictions to obtain the final decision of our ensemble. So you see that in this case we created a very simple, we've written very simple mathematical expression how we combine output of simple learners, and we get a more complicated learner that has a little less chance to overfit, because if you remember the data set that we looked at before, the probability that you will get outliers, probability you would get those rare red dots into the blue area would be low. So maybe only fraction of those learners of those trees will see those outliers, and the rest will know nothing about it. And so they will be quite confident that in this area there is nothing related to the red patches. So it would be able to rule out those outliers completely. So based on this bootstrapping, we can add an aggregation, and we get algorithm that is called bagging. So it is essentially what I described before. So from the data set we mentioned, we make splits, we train learners, and we combine those learners into a higher order decision maker. So let's take another example, another procedure that allows to mitigate overfitting. So as mentioned before, we can do bagging, but also we can reduce error by averaging over instances and features, over individual instances and over individual feature. So we can do this subsampling in a more clever way, or specific way. I would not call it clever. It's very straightforward. So the algorithm is the following. So we have a training sample XL here, and we iterate several times. So this n is picked rather arbitrarily. So we pick p random features out of all d features in our dataset. So d is dimension of the training sample, of the features of the vector of our feature. And then we make a bootstrap of this sample. So we pick some number of bootstrapping, and then we learn a decision tree using those bootstrapped sample. So we stop when leaves in our learner contains less than specific number of instances. And this is it. So it mixes different kind of features and mixes different kind of instances by bootstrapping, and makes ensemble of trees that are trained on different subsets of those. So here is an example. So we have 3 instances, and we have 3 3 features, and we have 5 instances. So here there are kinds of trees that we can build out of this. So this one is built on 2 features, A and B, and on instances 1, 1, 2, 4, 5. This is built on features A and C and those instances, etc. So it adds another dimension of randomness, and it is much less prone to overfitting. So it is much more stable in the end. And here is the illustration how input data is split into partition by different algorithms. So we consider decision trees, we consider random forest, and some other algorithm, quadratic discriminant algorithm. So you see that in general, picture of decision trees for different kinds of input data. So it's kind of, depending on the depth, it can go really nasty, but it's not very smooth, I would say. With comparison of random forest, you see that it is able to carve those white areas here, and it means that it is not certain about what should it do there, and there are areas where it can give very solid color. It means that it is quite confident about the decision it makes in those areas. Okay, so I think for the sake of time, I'm going to skip this, or maybe not. No, bias-variance tradeoff is very important here, notion to understand. So let's go into the piece of theory. So just a reminder of the notation. So we have a training sample XL, and we have our samples that are generated from a distribution that we do not know. And if we look at regression problem, so we worried about mean squared error loss that is denoted by Q. So it is a function of ground truth and the hypothesis prediction. And there is expected risk quantity. So it corresponds to the mean squared error with respect to the whole space of all possible values that we draw from a true distribution. So it is integral over this p over of p multiplied by error by all dimensions of our space. So it is an expected risk. So it is how nicely our algorithm behaves on the whole possible samples that we can get from the reality. Of course, we don't have the reality at our disposal. We have just a subsample from this distribution. And so we can make a statement that expected risk is minimized by the following expression. So it is just rewritten the same thing. And R here is quality of our hypothesis. So we have to find such a hypothesis that minimizes the risk. So it is optimal. It is the best possible hypothesis that we can get that minimizes the risk that we want to reduce. And then we can decompose the risk or error that our algorithm introduces in two different components. Now let's say we have the training sample and we have a learning method that gives us a hypothesis that we want to minimize, that we want to reduce risk of. So mu here is class of algorithms, so decision tree, random forest, linear regression, logistic regression, whatever. And so we can evaluate quality using average over possible samples in our training set. So we can say that the quality of our learning method is the following. So we just write all the things together. So it is integral over all samples that we have, over all space that we have, and this MSE term multiplied by probability and multiplied by all probabilities of getting items from the initial sample from the training sample. So it is quite complicated, but it is a true statement. And then we can rewrite it into the following. So we just can transform this into the following expression. So the following expression is this. So it is error that comes from the error of an ideal learner. So it is noise term that is there in our data. So even if we had an ideal learner, this term cannot be reduced. Then a bias term. So it is a learner approximation of the ideal algorithm. So it shows us how big the discrepancy from the model that we built from the ideal learner. So ideal learner is this guy. This is something that we cannot get. And the variance term is a sensitivity to sample replacement. So if it shows how big the variance is if we change the subsample that we evaluate our algorithm. And here is the illustration for these mathematical terms. So you can compare accuracy of the algorithm to the accuracy of the shooter. So you have a target here, and the ideal shooter can get to the center of this target, and you see that there are two measurements, 2 degrees that can characterize the misses. So in case you get into the center, there is no question, so you're great. But if you're missing the center, it may happen in quite different manner. And you see that there it is possibility that you get roughly into the center, but you have some kind of spread, some kind of variance around the center. So it is a mode when you have high variance and low bias. So low bias means that on average you get things right. But for specific instances, specific details specific instances, predictions may be a little bit different from the true label. And on contrary, there is another mode that is called high bias. So the sample is shifted from the center, and it could be shifted but very close to each other. So it means that we are biased by some external, some data or maybe algorithm. Most likely it could be both, or we could be biased and we might have high variance. So it is very important to understand what kind of errors do we have. Either the accuracy is low because you are here, or your accuracy is low because you are here. And maybe if you know where you are, it could be possible to adjust something in your algorithm. So from here, it's quite easy to get to here. So you just have to introduce some kind of adjustment, some kind of calibration. But from here, it is very difficult to fix. Well, and if you look at the example that we started to examine yesterday, so we have a degree of polynomial that we want to fit into the data. So here is the illustration of the dependence of the error depending on the model complexity. So it is a generic picture, so it is not 100% correlated with the one on the previous slide, but you see that there are usually different kinds of error associated with model complexity, or with this complexity in case of decision trees corresponds to the depth of the tree or number of nodes that we have. And in the beginning, the bias usually is very high, so we do not know what we are doing because we start from some random approximation, and in the end, the variance could be high because details start to matter a lot, and usually we can detect, and usually we have to stop somewhere here. And how to find this this place? We can just examine what is the dependence of the validation error with respect to the model complexity. So as soon as it starts growing, it means that we do not need to increase model complexity anymore. And we should not look at the training error because it always goes down. So it's usually it is used for model complexity is adequate to the problem that we have. The training error will become less and less. The applications or implication of the statistical analysis of bagging. So we can write that expression of the expected risk minimization. So bias in case of bagging algorithm is not worse than the initial one. I mean, the one that we get without bagging. So because of this math. So this term is expected risk that we get by bagging, and this is expected risk that we get by initial model that we train. So bagging doesn't introduce any biases. And if we look at the variance, so in case of bagging, the variance is n times lower for uncorrelated hypotheses. And it is not much of an improvement for highly correlated hypotheses. So that should not go into details. If you want, we can come back here. But it is a really important thing that explains why random forest works better than individual decision trees. So, and here is the like a small application of decision trees, multiple decision trees or decision tree algorithm. So if we have a high training error, we can check if the bias is high. So we can train longer, train a more complex model, obtain more features, or decrease our regularization, or maybe come up with a better model architecture. So, and if bias error is low, so we can check what is a cross-validation error. So, and if a cross-validation is high, it means that we have high variance, and we can fix it with adding more data, or decreasing number of features, or increasing regularization, or thinking of a better model architecture. So that's it. So let's state an intermediate conclusion. So what we saw about ensembles of trees. So bootstrapping is a general statistics technique for building learners that improve the performance of the model. Bagging is the way how you combine those weak learner algorithms by bootstrapping and aggregation. And random forest is bagging over decision trees with subsamples of the features that we have in our data. And important notion of bias-variance trade-off that allows to understand what's going on with our model and how can we improve its performance. So let's look how this boosting can be applied to a regression problem. wait a second. So if you have questions, maybe you can ask them now. Otherwise, we'll look at this regression part. Okay. So we want to, the labels are real numbers and we want to minimize minimum squared error. So we search for a solution in the form of weak learner composition that is a combination of learners. And we can use it by using boosting approach. So we start with a weak learner that is essentially a mean value of our ground truth training data, training sample of labels of a training sample. And then at step number n, we compute the residual from a weak learner and the ground truth. So these are residual. And then we learn the next weak algorithm using those residual as a target. And this is it. So this way, it is natural how you can combine those weak learners together, and you will see that by design, every learner on top of the previously built hypothesis reduces their mean squared error. So here is an example. So we have a set of dots and color of the dots here doesn't mean anything. So those are just dots. And we build a so-called regression tree. So regression tree is something that starts with a simple hypothesis 0. So it is essentially a mean value, and it can add some details to the difference between our ground truth and the and then the output of the previous learner. So in case we do this by a tree, so we make those weak learners implemented by a tree. They make a split over horizontal axis at some point. So we have the feature X here, and this is ground truth label. So and if we make the approximation by a tree, we have to make a split, and since it is depth equals to 1, it means that there are 2 different splits, and every split has specific value that it predicts. So I imagine that one split goes here, so we have left and right, and another split goes here. Also, we have left and right, and another split goes here. We have left and right. And after you subtract it from the ground truth, sorry, if you subtract those green line from the ground truth, you get something with less variance, and you build another decision tree that of the depth one that splits the data into partitions. So this would be initial split. This would be say the first left split. This would be the first right split. And you see that the numbers on vertical axis becomes less and less. Again, and now you look at the residuals once again, and you see that you can feed the tree learner into this data once again, and it would reduce the error more and more. So and in the end, you get this green line that consists of the output of 3 trees. So it is an ensemble of 3 trees working all together, sitting one on top of the other. Okay, so there are other extension of the decision trees algorithm that can be applied to the data, and there are different heuristics that allow to build those models, and sometimes they work better than random forest. I wouldn't say that adaptive boosting is really great performance, but it is quite an interesting idea and simple idea for making for building new algorithms. So let's take a bit closer look how it works. So once again, we have a training sample, and we search in a solution in the form of a weighted sum, where the final decision is performed by weaker learners weighted by some coefficients. And at every step, we extend our algorithm with a new hypothesis that is added to the tree. And the way how we choose the hypothesis and its weight is the following. So we measure fit quality using so-called exponential loss. It is different from the loss we had before. So it is exponent and the following argument minus ground truth to the multiplied by the output of the predictions. And if we want to minimize this loss, we can take a derivative, and out of these derivatives, we can conclude that the best learner is the one that minimize minimum squared error with weights Wi. That can be computed by the learners that we already have. So it is expression that we can compute. Given this, we can minimize the weight gamma n, which is another minimization problem that minimizes our exponential loss, and then we can also compute it by derivative, by computing a derivative. And here is an example how those algorithms work. So you again see that we have initial data set, and we have a split of that is performed by a weak learner, and here, so this is initial state. Then we build a initial. We compute the error, and this error magnifies misclassification quite significantly. So you remember that this quadratic exponential error. It means that sorry, it's exponential error. So it multiplies the error and takes it into the multiplies misclassification and makes exponent to this misclassification degree, power. So that's why dots here are depicted by larger circles. So it means that on the second step, it tries to tries to adapt to this misclassification and builds a different decision here. And then it adapts to this misclassification and builds a different decision here. And in the end, you get an ensemble of 3 learners that are depicted on the right. So this one, this is the second, and this is the third. So, and in the end, you get quite accurate classification here. Okay, so in the final example that is fundamental idea that that is used for many classification state-of-the-art algorithms nowadays in the field of decision trees. So probably you've heard about BDT, boosted decision trees. It is not purely boosted decision trees. It is actually built by gradient descent, the gradient boosted decision trees. And probably you heard about XGBoost, which is extreme gradient boosting algorithm. So it is also based on these gradient boosting ideas. They add a few tweaks to make it perform better. And another popular algorithm developed by Yandex and open source that outperforms XGBoost in many important cases when you have categorical features. That's where the name comes from. It is called CatBoost. It is also stands on the shoulder of gradient boosting. So let's take a look how it works. So imagine we have learners up to an-1. So now we have to find the next gamma n and hn, which minimize our loss function. And then the shape of the form of the learner is the following. So we can recall that the functions usually decrease in the direction of negative gradient. So and we can express our loss function as a function of z. So which we denote our current iteration tree as. And then we execute the gradient descent with respect to z. And we search for such splits, such wait a second. Those are derivatives of L that we want to compute. So those are approximate of the new learner, so approximate of this Z function. So and we want maybe come up with every instance that we have in our training sample. This idea of computing those SI approximates has been formulated by Friedman. It's called gradient boosting machine. So we have the loss in this initial definition of this algorithm. We have hyperparameters in terms of number of boosting iterations, in terms of loss functions that is differentiable with respect to Z, and we have family of weak learners that we can build. So we initialize this boosting machine with some zero hypothesis using very simple rule. So for example, just taking the most popular class as a default rule. And then we execute boosting iterations as many times as we specify. And then we compose the final learner through the combination of those individual ones. So every iteration is the following. So we compute those derivatives or pseudo residuals and learn the hypothesis by regressing into those residuals. So we build a learner that minimize minimum squared error or whatever minimum square error here. And then we find the optimal coefficient gamma n using plane gradient descent. So it works like this. And then we add this new learner to a previous iteration of gradient boosted machine. So this is pretty much it. So if we look at the example, how the output of such a regression look like, so you see that the curve may be pretty smooth. So sorry, it's so let's start. So it is a cosine with some noise added, and then we want to approximate it with 3 boosting iterations. So we specify quadratic loss, and the gradient of quadratic loss is very simple to compute. And then we, on every iteration, we pick a decision tree as a weak learner, and we want to be 2 is the depth of such a decision tree. So here is an example of this iteration. So this is our initial approximation, and then we on top of this we add something, add another tree of depth 2. And then we subtract it from the previous iteration and add a tree on top of this. And it can work quite nicely. I think I'd better show you the following interactive part. Just wait a second to take some time to load the web page. And while it's loading, I would also paste the link to the chat window because it's fun to play with this yourself. For some reason, it's working a bit slow. Okay, so now it works. So you see here I have a function, so I can pick from set of functions that I want to approximate by a decision tree. So usually we look at those functions from above, so something like this. So color here depends on just denotes the depth of the function, and then we want to build a tree on top of it. So if it is a tree depth 0, it is just a single split, zero split and mean value. So there are no splits for the tree of depth 0. So we just take a mean value of the target. If we add split, a single split, so we see it is split according along the line x2, and then we visualize it the following the following way. So if we rotate it a little bit, we see how it looks. And if we build a really complicated tree, it can approximate sophisticated shapes more and more accurately. Well, this would be an easy thing to approximate. So you don't need depth 3. Probably 2 would be enough to approximate it ideally. Okay, so this was a single decision tree visualization, and this one is gradient boosting visualized. So you have a shape, and you build an ensemble of 100 decision trees, and depending on the depth of those trees, you get more or less accurate approximation. Okay. And in this example, we can play with number of trees and play with the depth of individual tree. So you see how accurate your ensemble can get with adding more and more instances. So it shows here residual function that a tree tries to approximate. So residual and prediction of the next tree. So you can get pretty weird landscapes here. Okay, so I don't know why I cannot paste the link to the chat, but hopefully you can get it. Here it goes. The slides that I'm showing, I've applied to the Indico page already, so you can get it from there. So to regularize Gordian-Muster decision trees, we can introduce some randomness or random walk in the space of samples, and for complicated weak learners, when a few boosting steps may be already enough for overfitting. So we can regularize by changing the learning rate with the number of iteration. So you see that in the gradient boosting, it is important coefficient that we use to compute the gradient, and we can regularize this by adding one more coefficient. So it is a number from 0 to 1, and it effectively doesn't allow to far in the wrong direction. Okay. I think those are quite natural to follow. So with the shrinkage, what we get here, we get more shaky, training or learning curves, but it is eventually getting to much lower error. So you see that test with a subsample test subsample 0.5, it is this guy that goes pretty high, and subsample 0.5 and learning rate or shrinkage rate 0.1 is getting quite better results than initial test error depicted here by a red line. Okay, so this is it. There is a section denoted to XGBoost, but I'm not going to go into details. And if you want to explore this, I welcome you to look at this. And just a few more ideas to build a better decision trees takes into account second-order derivatives, and it penalizes large leaf counts by some regularization term that is added to the loss function when they compute the gradient. So it is exactly this guy. Yeah, and then the third is the choosing split by this impurity criterion. This is basically it. So let's make a conclusion here. So we looked at the boosting, which is a meta algorithm technique that can be applied to anything to build weak learners. And we can apply boosting for any kind of losses, any kind of problems. And that's a kind of approach that people quite frequently use to solve Kaggle challenges. The gradient boosting machine is a general approach to building learners on top of existing set of learners by using a gradient over the loss function. And there are extensions to this boosting machine called AdaBoost and XGBoost. And well, just a quick illustration how you can combine learners that are not coming from the same family. So imagine you have a two-dimensional space that you want to and you have you have darts that falling into a target, and you have different players, Bob, Kate, Mark, and Sue, and you want to identify who is who. So you have a training sample and testing sample on the right, and here is the link to the paper or to the blog post that describes how to combine two algorithms together. The first one is K nearest neighbors, and the second one is support vector machine. And so we can build those two algorithms using a training sample, and you see that the accuracy of the K nearest neighbors are roughly 70%, and accuracy of SVM is nearly 80%. They can be illustrated by the following colorful pictures. So color is just representation of the output of the algorithm, and you can build a stacking model by the following procedure. So you partition your training sample into 5 folds, and for each fold we do the similar procedure to cross-validation, and we feed each base model into the folds besides I and predict on fold I. And we save predictions of those models to build the features or build a metadata set. And then we train a model on this metadata set. So basically, we build something that needs to predict output given the ground truth given the output of the previous algorithm. And following this procedure, you get much nicer results. I think there should be a number as well. I don't know, where is it missing? So the accuracy of this model is higher than the accuracy of the previous guys, which is quite remarkable, and it is can be thought as an extension of this ensembling algorithm. But in previous ensembling, we just combined linearly output of the models, but in this example, we fed output of one model to the as input to another model. So that's why it is called stacking. So you build one model on top of each other. So, and this basically it. We looked at quite a range of machine learning techniques. Those are robust and quite powerful residual as around for a while, and despite the hype of neural networks, those are used quite actively in production scenarios because those are interpretable. Well, random forests are not as interpretable, of course, as individual learners, but anyway. And they are fast to train. They do not require expensive GPUs, and they allow to play with those models as a Lego blocks and build one on top of each other, and you can experiment which one does the best for your particular problem. So that's it. If you have questions, I would be happy to answer.
Hi, Andrei. I have a one. So this is maybe a bit specific, but it's one of the things that interests me. So one of the things you can do is when you compute your loss function, well, as you said, you can add regularizing terms, for instance, to avoid variance and things like, or to promote, variance and things like that. But you can also add additional functions that are useful for your user case. Like I'm thinking, for instance, if you want to reduce the correlation with a variable. So, for instance, in classifying problems of background versus signal, of signal versus background, we want to usually avoid being too correlated with the invariant mass of the objects. Yeah, I mean, I know this is a bit technical, but I think you know what I mean, right?
Yep.
So my question is, like, because I know that there has been some progress from and you are involved in part of that, but
there, and you will see that.
So is this is this the kind of thing that people is working on, or there's not much more you can do compared to what has already been done? For instance, I'm thinking in this UGB thing, something like that.
Yeah. So thanks for the question. I think I have a piece of slides somewhere besides about this. Maybe it would require. So it's not like 1 minute explanation. So of course it is possible to add regularization term that would penalize trees from picking some unwanted correlations, right? And it is not difficult to do with decision trees in particular. The thing is that this technique has been around for a while, and there is even a repository that allows you to just pick it. I mean, it's just a class that easy to start working with, like a scikit-learn compatible implementation. And there are neural network-based approaches that do similar things. And if you have a lot of data, I would say that neural network behave a little better. But if you don't have much data, then those gradient boosted approaches are doing quite nicely. But if you want, I can start tomorrow with this short introduction to this reweighting example, how you can apply boosting to this kind of problem.
Well, maybe that's a bit too specific for this course. So I think I will try to have a look at. I mean, yeah, I know the reference. I remember that you wrote a paper, so I would try to have a look there. I was just wondering if there was something newer than that, but that's fine.
Not I'm aware. Not that
Okay.
I'm aware
Okay.
of.
And then the other question that I have, if I may, it's concerns this well, the last thing you explained about this sort of blended algorithm, so trying to make use of several classifiers together somehow. So in principle, this looks like a good idea, right? But I tend to be sort of pessimistic about how this might help, in the sense that, well, at the end it's the same data, so it's hard to conceive that you can. I mean, I have the feeling that that adding additional classifiers that are essentially worse or weaker really helps a lot. But I guess this depends on its type of problem, right?
Well, actually, if you're talking about this example of staking that I had in the end, it is exactly what neural network does. But in case of neural network, the class of these weak learners is restricted by logistic regression. So essentially, a neural network is a logistic regression on top of logistic regression on top of logistic regression, and it could go on infinitely. Of course, there are many different kind of layers, like convolutional or recurrent layers, but they pick features from the previous iterations and try to do something meaningful. And in this example, I just was trying to show how it can work with algorithms that we looked at, and it's kind of a natural extension. I mean, so you see the output of one as the input for another, and it looks like not a terribly difficult thing to do. In neural network, okay, it is just performed in a pipeline without like training of a.
Yeah, I mean, this is stacking. You're right, but I was thinking something similar but correlated. Like whenever you have a new classifier that uses the output of other classifiers as features, to give you a new output, so it somehow makes use of the power of each of them individually. But yeah, I think it's pretty much the same. It's just that instead of doing them one on top of the other, you have all of them in parallel somehow. But,
yep.
Okay, thank you.
Welcome. Okay, so if there are no further questions, which I hope means that you are familiar with this topic, let's reconvene in 15 minutes, or like past 11. And we'll look at some hands-on examples. So we connect to the same room, right?
Yeah, same room.
Okay. Thank you very much. So see you soon.
Thank you, Andrei.
Thanks.
The output. horizontal. So, hello again, everyone.
Hello, Andre.
Yeah, let me start with the question. If you have any problems or concerns, or something that needs to be clarified regarding practical part of yesterday. Okay, so let's.
Sorry,
yeah.
one quick thing I was thinking now. Yeah, I'm sorry to be the same asking again. So
No worries.
One thing that, because yesterday you were explaining a bit k-folding, and I don't remember at the moment if this was part of the practical part or not, but I mean, this is very common in scikit-learn, for instance. But one thing that with k-folding that bothers me a bit, the way it's implemented in scikit-learn, is that you can only do k-folding in two pieces, right? You can only have one part for training and one part from testing, and then you iterate. But what happens if you want to have, because I mean, you may want to do k-folding in three pieces where you have one part for training, one part for testing, and one part for applying somehow, because it may happen that you have only, for instance, you have only one part of, you have only just one data set that you want to use for everything, and then you don't want to lose any single data for training or testing. So you can do this, this triple somehow folding. But is there a way to do that in scikit-learn? Because yeah, the problem that I found is that if I want to do some of the advanced features like grid search and these kind of things, then you have to give up a part of your data. In any case, I don't know if I made myself clear.
So in case you want to do hyperparameter optimization, usually yes, you have to separate another piece of data, of a training set of a data that you have. But I'm not sure about the triple folding scheme. To me, it looks like you need to separate one piece for final testing, and the rest you split between training and testing. So, or training and validation. And so you just split the data set in two, and then one of those you split into folds. Would it be an option?
Yeah, but imagine that you want to, I'm going to be a bit more specific. Imagine that you're doing a search in the LHC, and then you have wherever final selected data, and you want to use that to do your search, and you want to train a classifier that for which you train using for which you use as background the data itself. Then if you do what you say, you are giving up part of your statistics, which is bad. But then if you just use you cannot just use k-folding in that data by itself, because then you could have some sort of overtraining, at least in your choice of in your optimization of hyperparameters. So this is what concerns me a bit.
I'm not sure. So once again, you have a Monte Carlo sample that you use for training, right?
You can use, but yeah, use that as a signal. So, but for the background, you usually have to use the data itself.
Okay, yeah, use the data for the background, and so you split this background into two pieces. One you do for training and hyperparameter optimization and all the tuning that you want, and then you have a small, or well, the remaining part that you didn't show to the algorithm before, and then you use it for final quality assessment.
Yeah, and then yeah, whatever you have this half of the data that where you didn't use it, that you didn't use in the training at all, and you apply the algorithm to that part, and then you do the search there. But what happens with the first part of the data that you use for training? Then you can do the same thing in this. You can like swap both parts and do the opposite thing. But what I'm saying is that for the training, that's fine. It works perfectly. But for the hyperparameter optimization, then you could create two independent classifiers, one in each part of the data somehow. That's the only solution I see. Because if not, you would be always tuning or choosing your hyperparameters using a fraction of the data in which you use for the training. But maybe you can discuss offline. Maybe I'm not being too clear.
I'm not sure I see what is your problem.
Okay, no worries.
Even if you train a regular, so let me draw something. If I share the screen. So you should see a GitHub.
Yeah, I do, yeah.
Web page. Yeah, now I have, let me just open a blank screen as a whiteboard, blank document as a whiteboard. Okay. Just a second. So you have a data set, and you then split into a subset, into something that you don't want to show to algorithm. Oops. Let's call it testing. And then you build k-folding scheme here. Right, so you have 5 folds here, and you do all the training and hyperparameter search with this data set.
Yeah.
And afterwards you validate it on this part.
Yeah, yeah.
So what would be the problem? What kind of problem do you see? That you're afraid that you're losing statistics from this?
Yeah, the problem is that I want to use all my data set in my search afterwards.
Yeah, but then if you're happy with the quality here, so you train it, you use it just a few times, you found the right hyperparameters, then you pick the whole data set and train model on this whole data set.
Yeah, but the problem is that then I would have, then for the chunks in the left hand side, I would be using a classifier for which I chose the parameters using those that part of the data itself. You see what I mean?
I don't see why it's so it's a usual case when you do cross validation and test hyperparameters and whatever, and then you choose all the take the old data set for training a classifier, so you do not. I don't see the way how you can do anything better. I would say. Like
Okay.
this.
Okay. Okay. No, yeah. Thank you. I want to steal more time from for the rest of the stuff. So yeah, I will try to think of it more carefully. Thank you.
Okay. Thank you. Okay, so let's continue with the exercise. Oh, sorry. So you can either follow the collaboratory link from the GitHub repository. Let me share a link to the chat. Also, this link is in the Indico page of the event. There's chat window. So it shows me a list of notebooks that I have in my repository, and I have to pick. Let's start with decision trees and ensembles. Is it working faster for you? So did you manage to open the notebook in Google Colab?
Yes. Yes.
Okay. For me, I don't know why it's taking so long. Okay, here it goes. So let's recap what is a decision tree. So you see that there is a very quick engineering example how you can solve any problem with just tape and WD-40. And then let's continue with some code. So we start with importing necessary libraries. And then we generate a data set. And then we generate artificial data set. You see that scikit-learn has a lot of code that allows you to build an artificial toy data set. So in that case, we just create the blobs that contains 400 samples. It is two-dimensional, and we fix a random state here, so it will not go. It will be reproducible. So, and you see this data set here, red and blue dots. So decision tree sits in the namespace is called scikit-learn sklearn tree. We take decision tree classifier from there, and then the model selection subspace allows to give access to the train, test, split method that splits the data set into two. Then we define a method that just given the prediction of a classifier or a classifier itself builds a decision surface. So for every point on the space, in the space of the features, we get a prediction denoted by a color. Don't worry if it looks a bit complicated. It is just a visualization procedure. And if we train a model by instantiating a class decision tree classifier with parameter min samples leaf, so it basically says when should we stop growing a tree. And once again, we call fit method to find the best parameters for a given data set. And then we plot decision surface for this particular classifier. Oops, decision tree classifier is not defined. Sorry. Forgot to run this with cell. Now it should be better. Here it goes. So let's take a closer look at the tree that we've built. To build a decision tree, we just call a single method plot tree that take a trained classifier. And the second argument is just a denoting place where we want this picture to plot. Since we fixed a random state, the picture should not change. But anyway, so it shows you the internal structure of the tree. So if every block here corresponds to a tree node, and for every node you see what is the decision rule, what kind of feature, which feature do we use, and what is the threshold that we compare, and what is the Gini purity criteria that we measure on this level. How many samples do we have, and what is the how many samples do we get to the right and to the left? So for every node we have these characteristics. And so if you want to look at the decisions of the tree on the training sample we call predict method that returns an array of 400 zeros and ones. So we see how it looks, although it doesn't give us any meaningful insights. More interesting method that is corresponding to predict proba. So instead of giving 0 and 1, it gives us a vector of 2 numbers or numbers of classes that we have, giving the probability, or maybe not exactly probability, but weight that corresponds to this particular class for a given instance. So let's take a look at more complicated example of multi-classification data. So we load this data to the sample. Sorry, load this data into the notebook, and then we split the sample into equal size pieces, and then we train the model. Then we split XTOY. What should be? So those XTOY are just data set that we created previously. So this one with the blobs from scikit-learn. Okay, so now the task for you would be, to look at the decision boundary depending on the tree depth. So you can specify tree depth by max depth parameter of the decision tree class, and then you have to look through the various depths and look at the pictures that you get for different depths. Is it clear what you should do there? Okay, then I hope it is. Please take maybe 3-5 minutes to fill this gap in the code. You can mark in the chat window. I asked the question "Are you through?" So you can just add the reaction like thumb up or a smiley to denote that you're done. Okay, so did anybody manage to get the grid of those decision surfaces?
Please, can people confirm they can hear us at least?
That's also a good question.
I can hear you. I managed to get these grids. Not completely sure if I have done right, but I have it.
Yeah, but so you see the code here, it creates subplots. So it is essentially a sub picture, and you ask to create 5x2 grid of plots, and every picture there is represented by axis matrix. So it is something that you can use to plot the decision surface on. So you see that one of the arguments that you give to the decision surface method, just let me scroll back to it. It's getting pretty slow. So it takes axis, which is a space where you can plot your figure. So it is it's a final plot decision surface function, right? So essentially, you need to train a classifier on the same sample. We always use the same sample. The only difference is the depth of the tree. And then we pass the trained classifier to this plot decision surface function. And this is it. So let's write it down. Oops. In this particular cycle, in this loop, we have depth. So we initiate a create instance of decision tree classifier. Max depth equal to depth. And again, we can feed it into the data using the same line. X toy train, Y toy train. And this is basically it. We don't need to do anything more, just to call this plot decision surface function.
The other parameter there, min samples leave, should we leave that there?
Which one? Min samples. Yeah, well, you can leave it as it is. It doesn't matter for this exercise.
Okay.
I think that the Y is not capital letter, could be.
Yeah, right. It's not capital. I'm just trying to copy paste this line. I don't know why my browser is terribly slow today. Okay. And so I have to plot two decision surfaces here, because one should go for axis train, one should go to axis test. So X toy train and Y test axis train. Exactly. So I just copy the code, and instead of train, I pass a test. Oops. And I think this is it. So, and as you may have expected, depending on the tree depth, the tree tries to get into some unwanted regions, trying to carve examples that are not really nicely generalizable, because by design, all the plots that we have, all the dots that we have, they occupy like a circle area, like clusters, two clusters, and those regions on the bottom are not really relevant to those clusters. It is just a subsample outliers. Okay, now let's take a look at a better classifier.
Drake, can you show the code again?
Yeah, sure.
Okay, thank you very much.
Yeah. So now we'll try to adjust some parameters of decision tree classifier to improve the accuracy. So to examine all the parameters that we get here, we can just click Shift Tab, and it shows us what is the possible configurations. And now we're going to work with a multi-classification sample. multi-class classification sample. So you see we can play with different criterion for splitting. We can change the depth. We can change number of samples. We can change what is the minimum sample split, minimum samples in a leaf, maximum number of features, a maximum number of leaves in the node, and maximum number of leaf nodes in the tree, and minimum impurity decrease by making a split. So the goal is of this exercise is to try to see how different parameters are affecting the performance of the classifier. So when you see, we measure the accuracy on the test data set. So, and accuracy is depicted here on the top right. In the previous example, you see that we managed to, with a two-dimensional data set, we managed to get on the training sample up to 0.97. And on the testing sample, the best one was probably this one. So the depth number, the depth 3. So the accuracy on the testing sample was 0.71. Or not. Okay. The best one was the simplest one, 0.72. So let's see if we can get 0.72 for ourselves, or with simple depth equal to 1. This is not the case. And if we increase it to 5, we get a little better accuracy. Okay, and I leave it to you. So I'm already managed to get quite nice results that Z are higher than the 0.78. It was not difficult. Okay, so now let's move on to ensemble model. So we start with the random forest classifier, and also we can visualize decision surface because it doesn't depend on the model that we're using. And you see that this decision forest classifier consists of 100 decision trees, and we also specify that minimum sample in a leaf should not fall below 5. And this is it. And you see that colors now on this decision surface are looking much smoother, despite the blurriness and overlap between those between those classes. It still performs quite nicely. So now let's try more practical exercise, and we'll try to compute T statistics and p-value for hypothesis that random forest average accuracy is equal to decision tree accuracy on our toy multi-class dataset as a default rule. And then we want to explore it for two cases: whole test dataset and for a subset of 5 examples. So implementation of t-test statistics can be found at SciPy stats t-test int. So let's take a look at the manual. My browser allows. I should close all unwanted tabs. Okay, finally managed to get to the page of that describes this method. So essentially what it does, it takes two arrays of numbers, two arrays of numbers. In our case, it should be an accuracy of single decision tree and accuracy of a random forest. And it returns the calculated t-statistics and two-tailed p-value that we need to evaluate ourselves. So if we observe that large value, so we cannot reject the null hypothesis that the two samples are getting from the identical distribution. Otherwise, if p-value is smaller than our predefined threshold, then we can reject the null hypothesis of equal averages. So is it clear what we need to do here?
Can you repeat it, please?
Yeah, so we build two classifier predictions. So predictions for the random forest and prediction of the tree, the single decision tree. And so we do this for a toy multi-class test data set. Maybe decision tree, for decision tree, we also need to compare to cases when it is simple, like here, with no additional arguments, and case when we increase its depth to some meaningful value. And then we have to perform this to compute t-test statistics that gives us p-value of the hypothesis that predictions of the random forest and predictions of the decision trees are coming from the same distributions.
Okay, thank you.
Maybe can you post the link to the NumPy or the STP function that you commented?
Sure, sure. It is in the chat now. So here I computed that student test statistics for hypothesis that predictions are coming from the same distribution. And then you see that this hypothesis cannot be rejected. But the goal was to compute that average accuracy is the same. So to do this, it is maybe a little more complicated. Instead of computing, we have to split the data set into folds. So the test data set into folds, or those predictions into the same number of chunks corresponding to the same instances in our data, and then compute accuracy for every chunk of this data, and then you get the array of those accuracies, and then you run those accuracies through this student test, and then you get those value p value and value. Okay, so it's not difficult to do. Let's look at, and I'll send solutions afterwards, so you may have a look at this. Otherwise, feel free to do it yourself. So there is a family of different gradient-boosted decision trees that can support training on GPU and have quite extensive documentation and support. So most prominent one is called XGBoost. It's the most known, and it became famous due to the competition on finding a Higgs boson in 2014. It now supports multi-GPU distributed training. It can plot nicely trees that it created. And then it has some fancy features under the hood. Another one is called LightGBM. It is supported by Microsoft. So it is fast and memory efficient, supports GPU training, supports distributed training. And all the details that are behind this, you can find in the paper that has links there. Another example is called CutBoost. So it supports single node multi-GPU training. It also supports GPU-based inference, and it has built-in handling of categorical features. With those kind of features, regular splits are not very useful thing to do, because categorical features is something that doesn't have order in it. So it could be represented by integer numbers, but those integer numbers can be quite misleading, because you can think of those numbers as just some kind of hint that splits your data into different bins, but those bins are not necessary with relation with each other. So it could be a kind of tree or kind of flower that you're looking at, or kind of particle. You cannot compare. You cannot say that I make a split and every particle of identifier higher than 3 go into one bin, and everything with identifier less than 3 go to another bin, another subspace. Because, for example, if you have numbers, so if you have electrons with identifier 1 and photons with identifier 6, so probably they have something in common, but they will fall into different categories. So these kind of categorical features do not allow you to apply same splitting heuristic we've been talking about. And with such features, the approach that works is about computing some statistical quantities for every category. So for every category, you might be interested what is the ratio of those electrons in a signal sample with respect to the background sample. You also would compute those statistics for other kind of particles, and then you can use those statistics for making splits by a regular tree. And the CutBoost computes a multitude of those statistics and does it behind the scene. So you do not spend your time thinking about it. In physics, it is not very popular. So most of the features that you you can find are not categorical. They are real values, maybe with some example of integer where you count a number of hits or count whatever passes through the detector. But anyway, CutBoost has been used in LHCb, so it is one of the candidate algorithms, or sorry, not candidate, so it is used for muon identification phase of HLT triggering. So another detail about CutBoost is it uses oblivious trees. So here is an example decision tree on the left and oblivious tree on the right. So it's a little bit different way how the space is split. So by a regular tree, you split, and everything on the left of the first split becomes yellow. And here it's a little bit different. So you make a split in the coordinate 3 according to the first feature, and then again you can do split afterwards, and those splits afterwards kind of override what you get in the end. So it's not the best source of difference, but it is just a different way how to build those trees. And okay, this example allows you to train a CutBoost on a Higgs dataset, and since on Colab you can use both GPU and CPU, you can train those, and then you see how it compares, and with respect to time and with respect to accuracy. Okay. Okay, so there is one more note to the comparison with XGBoost. XGBoost doesn't complain when you do something nasty, passing some weird parameters. Okay. Here, few lines of code that allow you to compare different classifier performance: XGBoost, LightGBM, and CatBoost. And you could compare how different those models are on a Higgs dataset. And by the way, this Higgs dataset is coming from, let me check. So it is UCI archive 2.6 gigabytes that has been created to demonstrate that deep learning models based on neural networks can outperform regular decision tree based algorithms. Okay, so this is something that you then have to go through. I believe it is straightforward. If you encounter with any problems and any difficulties, you can let me know via email, or we can discuss those difficulties tomorrow. My email is in the chat window now. Okay. So if you have questions now, please give it away. Otherwise, we will reconvene tomorrow in the morning.
So then if there is no question, then we recombine tomorrow at 9.
Yeah, okay. Thank you very much. Have a nice day.